In 1998, a Chinese travel company bought a rusting Soviet aircraft carrier for $20 million and told the world it was going to be a floating casino in Macau. It never became a casino. For roughly 16 months, that hull sat trapped in the Black Sea, while Turkey refused to let it pass through the Bosphorus. Ankara cited navigational safety. Almost nobody believed that was the whole story, because Washington had made its position on the sail very clear. The ship had no engines, no rudder, no propellers. It had to be dragged across the world behind tugs, and at one point it broke loose in a storm in the Aegean and drifted for days while salvage crews fought to catch it. When it finally reached Dalian in 2002, the men who had bought it were staring at a problem far larger than a ship. They had no aircraft that could use it. 23 years later, on the 22nd of September 2025, the Chinese Navy announced that a fighter called the J-15T had been thrown off the deck of the carrier Fujian by an electromagnetic catapult, flown, returned, and been caught by an arresting wire. A launch and a recovery, both verified. And the single component that made that possible is small enough to hold in two hands. Underneath the nose of the J-15T, between its twin front wheels, there is a short metal bar that reaches down toward the deck. That bar is where a warship grabs a fighter and hurls it into the sky. Everything else in this story, the embargoes, the blocked sails, the stolen-looking prototype, the purged admirals, the decades of machining and riveting, funnels down into that one piece of metal and whether it holds. This is how China built a carrier fighter that almost nobody wanted them to have. Start with the aircraft that didn't exist. When the Varyag arrived in China and slowly became the carrier Liaoning, Beijing needed a heavy carrier-capable fighter. The Su-33 had been designed for Soviet carriers. It had the folding wings, the strengthened gear, the arresting hook. China wanted it. The deal collapsed. Reporting from the period points to a dispute over volume. Moscow wanted a large production order. Beijing wanted a small initial batch. And behind that, a growing Russian anxiety that anything sold to China would be studied, copied, and eventually sold back into Russia's own export markets. That anxiety wasn't paranoid. It had already happened with other airframes, and it would poison Russian-Chinese defense trade for years. So China went around Russia. In 2001, Chinese representatives acquired an unfinished Su-33 development prototype from Ukraine, an airframe that had never entered service and had been sitting at a test facility. It was not a production aircraft. It was not accompanied by drawings, tooling, or manufacturing data. It was a shape and a set of mechanisms to be measured, understood, and rebuilt from the inside out. Moscow's reaction was open irritation. Russian officials complained publicly about unlicensed copying when the J-15 emerged. But there was no legal instrument that could stop it, because the aircraft had come from Kyiv, not Moscow, and the Soviet Union that had originally designed it no longer existed to enforce anything. Now stack the second political wall on top of that. Since 1989, both the United States and the European Union have maintained arms embargoes on China. That closes off Western engines, Western avionics, Western catapult technology, Western carrier expertise, the entire mature ecosystem that the US Navy had spent 70 years building. Every attempt over the years to soften the EU embargo, which means the J-15 family was never really a procurement program. It was a reverse engineering and industrialization program conducted under sanction, using a prototype from a third country against the wishes of the original designer. That is the context you have to hold in your head when you look at a modern J-15T rolling out of a Shenyang plant, because it explains why the manufacturing story is the story. The aircraft is built by Avic Shenyang Aircraft Corporation for the Chinese Navy. Its outline is unmistakable. Single cockpit, twin engines, canards ahead of broad swept wings, twin vertical tails, folding outer wing panels, and an arresting hook under the rear fuselage. The letter T marks the catapult version, and the visible difference from the earlier ski jump aircraft is precisely that launch bar under the nose, plus the reinforcement around the nose landing gear that has to survive being yanked. The actual J-15T production line is not open to the public, and it would be dishonest to pretend otherwise. But Shenyang has publicly described the methods it uses across its aircraft work: computer-controlled machining, automated drilling and riveting, cable and pipe installation, precision inspection, and qualified metal additive manufacturing. That's enough to reconstruct the build honestly, without inventing secret rooms. It begins before the aircraft has a shape. Machined fittings sit beside formed panels: brackets, hinges, ducts, fastener holes. Every one of them tied to a drawing that controls not just geometry. Some complex parts can now be produced by metal additive manufacturing. But printing the shape is the easy half. Shenyang's own engineers have described the qualification work that follows: material data, process data, and testing, all required to prove that the thing coming off the machine is not merely the right shape, but an acceptable aircraft component. That gap between looking finished and being qualified runs through the entire program. A bracket can look complete while its dimensions are still under inspection. A hole can sit millimeters from where it should be and still prevent two large structures from ever mating correctly. Aircraft assembly is the accumulation of thousands of small errors across thousands of interfaces. Workers fight that accumulation with fixtures, measured reference points, controlled drilling, controlled riveting. The goal is never just to make parts fit. It's to make the finished structure carry loads along the paths the designers intended. Because in a few years, a catapult is going to pull on the nose of this thing, and a steel wire is going to grab the tail and stop it in a couple of 100 feet. Subassemblies come first. The forward fuselage builds around the cockpit and the nose gear bay. The center structure carries the wing roots and the widely spaced engine nacelles. Wing sections receive internal ribs, skins, control surfaces, and the joints that let the outer panels fold, until their alignment can be controlled against the central airframe. Then comes major joining, and the scale of the work changes. Large fixtures hold the fuselage sections, while technicians establish position, measure alignment, drill final holes, and drive permanent fasteners. Canards, wing roots, nacelles, and the twin-tail foundations all have to hold a very specific geometry. These aren't styling details, they're the anchors that keep the aircraft's identity and its aerodynamics stable as the build progresses. But a recognizable airframe is still not a carrier aircraft. What separates the two is a set of mechanisms that exist for one reason. The runway moves, it pitches, it rolls. It is a few hundred meters long, it is crowded, and it is surrounded by ocean. The folding outer wings shrink the aircraft's footprint for deck parking and hangar movement. Their hinges and locks have to hold flight geometry when extended, then release and fold in a controlled way on a moving deck. Public accounts of the J-15 program name wing fold manufacturing and assembly as one of the carrier-specific problems solved during development. And that makes sense, because a fold joint is a contradiction. It's a movable mechanism that also has to behave like a continuous, load-carrying flight surface. At the other end, the arresting hook solves the opposite problem. The catapult accelerates the aircraft. The hook stops it. On landing, the hook drops, strikes the deck, and catches a wire. A Shenyang engineer interviewed beside the J-15T described impact, overload, and wear as the central design concerns. That's the language of a component that gets hit hard, repeatedly, for a service life. Have to take a sudden, enormous pull and pass it into the airframe without becoming the weak link. And then the nose. The twin-wheel landing gear is visibly strengthened, and the launch bar connects the aircraft to the ship's catapult. That bar is not a towing handle. It's half of a controlled interface between an aircraft and a warship, which means its geometry, its pivoting motion, its clearances, and its attachment structure all have to be installed and verified as one integrated system, on the aircraft side, before the ship side ever matters. If you like engineering stories where one small detail explains an entire machine, subscribe to Momentum now. We're only halfway through this one. With the carrier mechanisms in, the airframe can finally receive the systems that turn structure into an aircraft. Engines go into the separated rear nacelles, cockpit equipment, electrical cables, pipes, ducts, sensors, and access panels fill spaces that were open a week earlier, which is the unglamorous, enormously expensive reality of every modern combat aircraft. The engines deserve their own political footnote. Chinese fighters depended on Russian AL-31 engines, and Moscow's willingness to keep supplying them was leverage. Domestic engine development, the WS-10 family and its naval derivatives, was the program that removed that leverage. J-15 variants have moved to indigenous engines, which matters far beyond thrust figures. It means the aircraft can be built at whatever rate China chooses, in a war, without a phone call to Moscow. Once the systems are in, finishing begins, and finishing does not erase the engineering underneath. Exterior panels have to fit around access points. Control surfaces have to move through full travel. Folding wings have to lock in both positions. Landing gear and hook get cycled. Electrical and hydraulic systems get checked. Measurements verify alignment and clearance. Only then does the light gray paint and the final markings go on. And completion is still not acceptance. Ground checks put weight on the gear and expose leaks, interference, and binding that no static component inspection would catch. Taxi trials exercise steering and braking. Engine runs test the aircraft as a connected system. Flight acceptance puts the structure into aerodynamic loads that no factory fixture can reproduce. Then the whole thing has to be handed to a ship, and that ship had its own political war. The Fujian is China's third carrier, and its first with a flat deck and catapults. The decision to go there was not obvious. The conservative path was steam catapults, the technology the US Navy had used for half a century. The radical path was electromagnetic launch, which the Americans had only just fielded, and which had given them years of reliability headaches. Chinese sources credit Ma Weiming, an electrical engineering academician, with pushing the Navy to skip steam entirely and build a medium-voltage integrated electrical system capable of powering an electromagnetic catapult. Accounts describe internal resistance and considerable professional risk in that argument. Whether every claim made about the resulting system holds up is something outsiders cannot verify. But the visible outcome is a flat-deck carrier with catapult tracks and aircraft coming off them. Because that's the payoff of electromagnetic launch, and it's a genuinely strategic difference. A ski jump forces trade-offs: fuel or weapons, rarely both at maximum. Official Chinese reporting says catapult launch allows the J-15T to leave the deck with full fuel and armament. A carrier air wing that can launch heavy aircraft at range repeatedly is a different instrument of state power than one that can only launch light ones near home. On the 22nd of September 2025, the Chinese Navy announced that the J-15T, the stealthier J-35, and the KJ-600 airborne early warning aircraft had all completed their first catapult launches and arrested landings aboard Fujian, and that the training had verified compatibility between the carrier's launch and recovery systems and multiple aircraft types. That last phrase is the one that matters. Fujian was commissioned on the 5th of November 2025, and the J-15T went back aboard for repeated catapult takeoffs and landings during the formation's early training at sea. Look at what the airframe now has to survive, over and over, for decades. A pull from the nose during launch, an impact through the landing gear on recovery, an arresting load through the tail. 3 completely different violent events, in different directions, on the same structure. That is why the launch bar, the fold joint, the landing gear, and the hook all belong in the same manufacturing story. They are one continuous load path, with a ship at one end and a wire at the other. And that is also why none of this could be bought. Carrier suitability cannot be added with paint, or markings, or a bolt-on hook. It reaches into the primary structure, the gear, the folding surfaces, the deck handling procedures, the inspection regime, and the relationship between a specific aircraft and a specific ship. Which is exactly why the embargoes were imposed in the first place, and exactly why they delayed this outcome by years rather than preventing it. There is one more political layer, and it's uncomfortable. Senior figures including Miao Hua, a naval political commissar who sat on the Central Military Commission, were removed amid corruption investigations, and further removals followed at the very top of the CMC. A navy can commission a carrier and lose its admirals in the same year. Hardware and command are not the same thing, and the second one is much harder to inspect from the outside. The closest functional comparison to the J-15T is the F-18E Super Hornet. Single-seat, twin-engine, carrier-suitable, multi-role. But the useful comparison is not thrust or radar. It's that both aircraft prove the same unforgiving principle, that a carrier fighter is defined by what happens at 4 interfaces, and everything else is negotiable. So the answer to the question we opened with is visible, and it's physical. The J-15T becomes ready for electromagnetic carrier operations by controlling the load path from its smallest qualified part to its largest assembled structure. Precision machining and fastening establish the airframe. Systems integration and acceptance turn structure into an aircraft. And launch and recovery aboard Fujian prove that all of it works together. 27 years after a rusting hull was blocked outside the Bosphorus, by a country acting on someone else's pressure. The most revealing object in the entire program is still the smallest one, where decades of embargo, reverse engineering, industrial policy, and internal political warfare finally meet the deck. Here's the part worth arguing about in the comments. Was the embargo a failure, or did it simply cost China 25 years it can now never get back? Tell me which one you think it is. Follow Momentum now for more evidence-based journeys into the machines behind modern power.